Guys, only 17 of you are present now. That is too low. We need more of you to be present to be able to start the class. So please notify your friends, your classmates. So guys, now today our subject of discussion is 1D wave equations. Up to this point, we only learned about 1D heat equations. Now, in Note 5, we are getting familiarized with a different PDE, a new PDE, which is very applicable, has lots of applications, and is a very famous PDE. Now, section 4 of your notes is one-dimensional wave equations. Now, the PDE for the wave equations is a PDE like this. Rho 2u over rho t2 is equal to alpha 2 rho 2u over rho x2. Now, you remember that in the 1D wave equations, 1D heat equations, we on this left-hand side of the equation, we had rho u over rho t. Now here we have rho 2u over rho t2. Yes? Now, in 1D wave equation, what is the meaning of u of x and t? The function that you're looking for in this PDE is u of x and t, and u of x and t denotes the vertical displacement experienced by the string at the point x at time t. Now, look at this figure in page 2 of note 5. If you have a string of length equal to L and you tie that string at both ends, here at x equal to 0 and here at x equal to L, and you make that string vibrate just like a guitar string, okay? Then u of x and t is the vertical displacement of the string from the equilibrium line at point x and at time t. Understood? Now, the alpha 2 that you see in this PDE is what? The constant coefficient alpha 2 appearing in the equation above is given by T over rho, in which T is the tension in the string and rho is the mass per unit length of the string material. And the value of alpha 2 is going to be given to you just like the alpha 2 in the heat equations. Now, after we have this PDE, which is the one-dimensional PDE, one-dimensional wave equation, in order to solve the PDE, we're going to need a couple of things. What do we need? A couple of boundary conditions and a couple of initial conditions, right? Now, can anybody tell me how many boundary conditions do we need in order to solve this PDE? Somebody. Exactly. Exactly. Thank you very much. We're going to need two boundary conditions plus two initial conditions in order to solve this PDE. Now, here is the difference, the major difference between the wave equations and heat equations. Here, it is not enough to have only one initial condition. Here, we need actually two initial conditions in order to be able to solve this. If you don't remember, let me repeat that. The number of boundary conditions that we need in order to solve a PDE is equal to the order of derivation with respect to the space variable, which here is x, and the number of initial conditions that we need in order to solve a PDE is equal to the order of derivative with respect to time, which here is equal to 2. So we need two boundary conditions and two initial conditions. Now, the boundary conditions that we might have when we are trying to solve this PDE can be anything. Those can be Dirichlet boundary conditions, can be Neumann boundary conditions, can be mixed boundary conditions, can be type 5 or periodic boundary conditions. They also can be Robin boundary conditions or any other type of boundary conditions, right? Now, as I told you, in order to solve this PDE, we also need two initial conditions. Now, let us read this paragraph. The one-dimensional wave equation, unlike one-dimensional heat equation, is of second order with respect to t. So here we need two initial conditions to be able to solve it. One of these initial conditions is the initial position of the string, which tells you u at x and 0 is equal to f of x, just like the 1D heat equations. And the other initial condition is the initial velocity of the string. Okay? So, the initial position of the string, which is in the form of u at x and 0 is equal to f of x, and the initial velocity of the string. But what is the velocity? From the physics, you remember that velocity is derivative of the position with respect to time, right? Velocity is the derivative of the position with respect to time. So, the initial velocity is going to be the derivative of u with respect to t at the initial time, which is usually t equal to 0. So, the second initial condition, which is the initial velocity, is giving you rho u over rho t at the initial time. And the result might be any function, which we call g of x. Okay? Here you know that f and g are given functions. So, the first initial condition, we call it the initial position. The second initial condition, we call it the initial velocity. Okay? Are we good? Questions? Guys, are you awake? Guys, let me give you a piece of news. Next week we're gonna have a quiz. Okay? Next week, inshallah, we're gonna have a quiz. So please try to be ready. And these quizzes are important because it is not apparent whether or not we're gonna be able to take exams. These quizzes might have a lot of role in your final grade. Now, guys, we are at page 4 of note 5. Here we have a one-dimensional heat equation, and by considering various boundary conditions for this 1D wave equation, we're going to have various types of 1D wave equation, just like the 1D heat equation, right? Now, just like the heat equations, 1D wave equation type 1 is a 1D wave equation with Dirichlet boundary conditions, right? Now, this is our PDE. These are our boundary conditions, which are of Dirichlet type, and these are the two initial conditions that we need. The first one is the initial position, and the second one is the initial velocity of the string. Yes? Now, let's go ahead and try to solve it. Here also, the method that we choose to solve this PDE is the method of separation of variables. So just like the uh, heat PDEs that you saw, for wave PDEs also, we start by assuming that the function that we're looking for can be written in the form of the multiplication of a function depending only on x and another function depending only on t. Now, if we differentiate this u two times with respect to t, we're going to have f g double dot. And you remember that dot means derivative with respect to time, right? And for round 2u over round x2, you see that it is equal to f double prime times g. And you remember that prime denotes the derivative with respect to x. Now, if you replace these two into the original PDE that you had, which was a wave PDE, and you divide both sides by alpha 2 fg, then what happens? Then you're going to have something like this. G double prime, sorry, G double dot over alpha 2g is equal to f double prime, oh, is equal to f double prime over f. And here, just like all the other cases that you saw, one side depends only on t, and the other side depends only on x. So the only way for these two to be equal to each other is for both of them to be equal to a constant. And we named that constant, and we name it here as the separation constant. And we usually write the separation constant as negative lambda. Now you see why did we do that, why we did that. The reason was that the separation constant usually turns out to be negative. So if we consider it to be equal to negative of something, that thing usually turns out to be positive, right? As you saw in all the heat equations that you solved. Now, this is the step one in solving wave PDEs. The second step is just like the heat PDEs, is to translate our boundary conditions to conditions in terms of F. Guys, questions? I'm not seeing any reaction from you. Kayvon, are you there? Yes, good. Mohammed Suleiman, are you there? Enes, are you there? Binay, are you there? Mohammad Zahir, are you awake? Very good. Guys, if you have any questions, please don't hesitate to ask me. Now, the process of. Go ahead. I answered. Yeah, yeah, yeah. Yeah, yeah, yeah. I answered. Whose name? Who are you? Khavan? Oh, Khavan. You have this course with me? Okay. No, I didn't write. I'm not doing presence and absence. I just wanted to see how the guys are doing. Now, okay, your name is on the list, inshallah. Don't worry. No problem. You're welcome. Guys, I didn't read all the names. Huh? That this means that you weren't listening. No, you weren't. Oh, okay, okay. So, guys, if you have any questions about the subject, please ask me. What is going on? Jihad, I know Jihad. You are here, Havan. Yes, these guys who are saying that I'm here are the guys who weren't listening previously. That is apparent to me. Havan, why aren't you listening? Jihad, where are you? So, guys, let's continue. Now, in step 2, just like the heat equations, we translate the boundary conditions to conditions in terms of F. Now, the boundary conditions that we have are Dirichlet boundary conditions. So we go through the process of translating them to conditions in terms of F. And for the first boundary condition, we see that it means that F at 0 has to be equal to 0. And for the second boundary condition, also, we're going to see that F at L has to be equal to 0. Now, guys, we have to solve this space ODE, which is F double prime over F equal to minus lambda, with these two boundary conditions for F at 0 equal to 0 and F at L equal to 0, with, with considering various possibilities for lambda. Now, please pay close attention. This part is very important. Now, if lambda is negative, when we were dealing with the heat equations previously, we usually used the time ODE in order to show that lambda can't be negative, right? Over there we said g dot over alpha 2g is equal to minus lambda, so g is equal to e to the minus lambda alpha 2t times a constant. So if lambda is negative, then the exponent of this exponential function is positive, and that means that as time goes to infinity, g goes to infinity, so u goes to infinity, and that is impossible. So in the heat equations, for the case where lambda was negative, we used the time ODE to show that lambda can't be negative. But here in the wave equations, we cannot do that because the time ODE is a second order ODE just like the space ODE. So it doesn't help at all to refer to the time ODE here. We have to solve the space ODE by the old way that we know. Now, let me answer your chats. Now, so we said that we have to solve our space ODE by the old way that we know, and that is to get referred to those initial equations that I included in the beginning of note 2. Now, when f double prime plus lambda f is equal to 0, then f is equal to c1 hyperbolic cosine of a square root of minus lambda x plus c2 hyperbolic sine of a square root of minus lambda x when lambda is negative. Now, if f at 0 is equal to 0, it means that c1 hyperbolic cosine at 0 plus c2 hyperbolic sine at 0 is equal to 0, and hyperbolic cosine at 0 is equal to 1, and hyperbolic sine at 0 is equal to 0. So this left hand side is equal to c1. So we conclude that c1 is equal to 0. Now if f at L is equal to 0, f of x with c1 equal to 0 is equal to c2 hyperbolic sine of a square root of minus lambda L. Now you see that this hyperbolic sine here can't be equal to 0 because a square root of minus lambda times L is not equal to 0. And hyperbolic sine is 0 only when the argument that it has is equal to 0, right? From this, we can conclude that C2 has to be equal to 0. Now, C1 is equal to 0 and C2 is equal to 0. That means F is equal to 0, which means U is equal to 0. And that is undesirable. So, you see that lambda can't be negative, right? Because lambda being negative leads us to have u equal to 0, right? So, guys, please pay attention. For 1D wave equations, this is how we show that lambda can't be negative. We can't get referred to the time ODEs that we have. Okay? Now, what about 0 lambda? If lambda is 0, means f double prime is equal to 0, and that means that f of x is equal to ax plus b. The first condition on f tells you that B is equal to 0. Go ahead. No, can't be shown. Mohammed, is that you? Look, Mohammed. Here, imagine that we wanted to use it with the time ODE. Huh? What would happen? We would have G double prime over alpha to G equal to minus lambda. And that is what? That is G double prime plus alpha to lambda G equal to 0. Right? Do you agree, Mohammed? Let me write it here. I'm opening up a Word file. So, let me share this Word file with you. So, guys, are you seeing this Word file? So, this was Muhammad's question. Now, the answer is this. Let us try to do that and see what happens. Now, if we try to use the time ODE, what is the time ODE? It is something like this.
Sir,
What is it?
why do you use a word for typing your screen and Zoom have a pen? You can write it by pen.
I don't have a pen. Oh.
By hand, do it by hand. I'm doing by hand. Like,
It doesn't turn out to be okay. Oh, oh, it will look ugly, I think. Oh,
okay, as you like.
no problem. So, can you clear this up, Vinay?
Okay.
Thank you. So, guys, you see this? Now, this is a very important question. That is why I'm elaborating on it. Uh, now, if g dot, if Imagine that we are trying to use the time ODE to show that lambda can't be negative. Let's see what happens. This is actually equal to plus alpha 2 lambda g equal to 0. Now, Muhammad, what can we do here? Here we can't do anything because this time ODE that we have is also of second order. The only thing that we can say is that g of t is equal to c1 hyperbolic cosine of a square root of minus lambda alpha t plus c2 hyperbolic sine of a square root of minus lambda alpha t, right? And from there, we can't make any conclusion on g, right? Because we don't have any initial condition for g, we have nothing. Over there in the for guys, the time is over. Let me send you another meeting link. Mohammed Abdul Razak, are you there? So guys, Mohammed asked a very important question, and it was, why don't we use the time ODE to show that lambda can be negative for wave equations? Now, we were elaborating on that. Now, we said that if g double prime over alpha 2g is equal to minus lambda, then g double prime plus alpha 2 lambda g is equal to 0, and that means that g of t is equal to, what does that mean? That means g of t is equal to c1 hyperbolic cosine of alpha times square root of minus lambda t plus c2 hyperbolic sine of alpha square root of minus lambda, a hyperbolic sine of alpha times the square root of minus lambda t. Now, Mohammed and everybody else, what does this tell us? Here, can we conclude that when t goes to infinity, then gt goes to infinity? Now, here can we conclude that? Can we conclude that gt goes to infinity when t goes to infinity when gt is equal to this? Guys, where are you?
I think yes,
Why?
because both cosine hyperbolic and sine hyperbolic it goes to infinity.
But what about c's? The c's might be somehow reversing the effect of each other. Your answer was very good. It's a very good idea, but you didn't consider the effect of C1 and C2. Maybe somehow they reverse the effect of each other, right? So maybe C1 and C2. So the answer is no, right? For the for the heat equations, our life was much easier because over there we didn't have this stuff. For heat equations, we didn't have g double dot over alpha 2g equal to minus lambda. We just had g dot. Oh, uh-oh. Let me get back to the Word file. Over there, we had g dot over alpha 2g g equal to minus lambda. So the time ODE was this, and the solution was C1 e to the minus alpha 2 lambda t, and we could say gt goes to infinity when t goes to infinity. But here, because of the different solution that we have for gt in the time ODE, we can't say that. So this is what you have to keep in mind. This is very important. Okay, guys, please do a print screen and save this Word file. This is very important. Okay, now let's go back to the original note that we're working on. Let me answer the chats. Okay. Now, guys, are you with me? We were considering the case in which lambda was equal to 0. If lambda is equal to 0, it means that f double prime is equal to 0, meaning f of x is equal to a linear function. Now, considering the conditions that we found on f, we can say that b has to be equal to 0 and a has to be equal to 0, and that means f has to be equal to 0, which means u has to be equal to 0, and that is undesirable. So lambda can't be equal to 0 either. Now, we reach to the main case, the case in which lambda is positive, right? Now, if f double prime over f is equal to lambda, or f double prime plus lambda f is equal to 0, then f of x is equal to c1 cosine of the square root of lambda x plus c2 sine of the square root of lambda x, right? Now, considering that f at 0 is equal to 0, if you replace it into this equation, we're going to get c1 cosine of 0 plus c2 sine of 0 equal to 0, and that means that c1 is equal to 0. Now, the second condition on f tells us that it is equal to 0 at L. Now, considering that c1 is equal to 0 and f is equal to c2 sine of the square root of lambda x, just like all the other cases that you saw in heat equations, either c2 is 0, which is undesirable, or sine of a square root of lambda L is equal to 0, which means that square root of lambda L is equal to n pi, which means that lambda is equal to n, which means that lambda is equal to n pi over L to the 2. Okay? Guys, please pay attention here. Here, as you know, these values that we find for lambda are called what? These are called eigenvalues, right? Now, instead of writing n pi over L to the 2, here we write lambda n to the 2, okay? For every n that is equal to a positive integer, right? When we do that, f of x, which was equal to c2 sine of n pi over Lx, will become c2 sine of lambda n x for every n that is equal to a positive integer. Okay? Now that we found the values for lambda, it is time to consider the time ODE, right? Just like what we did for the heat equations. In the case where lambda was positive, after finding f, we have to find g, and we can find g through the time ODE. Now, g double dot over alpha 2g is equal to minus lambda. Lambda is equal to lambda n to the 2, so we write minus lambda n to the 2. G double dot plus lambda n to the 2 alpha to the 2, g is equal to 0. That means what? That means g of t is equal to a constant times cosine of lambda n alpha t plus another constant times sine of lambda n alpha t, right? So guys, please pay as much as attention as you can here. Look, the equation 129 is a special equation. You see here that the solution to the time ODE here for wave equations becomes a cosine and sine function. But you saw that the solution to the time ODE for heat equations was a exponential function. So the exponential function that you saw is long gone, and for the wave equations, we're gonna see sinusoidal functions, right? Guys, this is very, very
Sir, sorry,
important.
question.
Go ahead, Lana. Go ahead.
Sir, for the G function, why we write minus lambda n square? I mean,
Oh,
in the
yes.
beginning or
Yes,
something.
yes, yes, yes. Look, G double dot over alpha 2G was equal to minus lambda, right? Do you remember?
Yeah, I remember.
Here. At the end of step 1, G double dot over alpha 2G is equal to minus lambda. Now, at the middle of step 2, after finding the eigenvalues, we decided to write, instead of m pi over L to the 2, to write lambda n to the 2. So lambda here, look, lambda is equal to Lana. Lambda is equal to lambda n to the 2, right?
Okay.
Did you understand?
Yeah, I understand. Thanks.
No problem. Very good. You're welcome. So f of x is equal to this, and g of t is equal to this. Now, by multiplying f and g, we find one answer for u. U of x and t equal to f of x times g of t. If you multiply these two, we're going to have C2k1 cosine of lambda n alpha t sine of lambda n x plus C2k2 sine of lambda n alpha t sine of lambda n x, right? And these coefficients C2k1 and C2k2, we are going to rename it when we are summing up all the solutions that we found for u. Using the superposition theorem, we can write u of x and t is equal to sigma n from 1 to infinity an cosine of lambda n alpha t sine of lambda n x plus bn sine of lambda n alpha t sine of lambda n x, right? So guys, you see that the solution that we get for u at the end of step 2 is radically different from the solution that we get at the end of step 2 for heat equations, right? The nature of solutions for wave equations is much, much different from the nature of the solution for heat equations. Here you have sine of something x times the solution to the time ODE, which is a cosine term plus a sine term. Okay? You have to be very careful here. Now, what is what else do we need to do here? In this equation, which was the solution at the end of step 2, there are two sets of undetermined constants. The first one is an and the second one is bn. How do we determine these undetermined constants? Using the initial conditions. Now, we had two initial conditions, if you remember. One of them was the initial position, and the other one was the initial velocity. Now, knowing that u of x and t is equal to this, we should calculate an and bn using the initial conditions. We use the first initial condition and write u at x and 0, which is equal to sigma n from 1 to infinity an sine of lambda n x equal to f of x, right? Why this is true? Because if you put in 0 instead of t into equation 131, these cosine terms are going to turn into 1, right? And these sine terms are going to turn into 0. So what you're left with is this part only when cosine is equal to 1. So you're going to get sigma n from 1 to infinity an sine of lambda n x, right? Now, if we want to determine an, the process is just like what you had in step 3 of all the heat equations. You have to multiply both sides of this equation by sine of lambda mx, right? If you remember, lambda n was equal to n pi over L, right? So lambda m is going to be m pi over L. If you do that and then integrate over the domain from 0 to L, what's going to happen? You'll have sigma n from 1 to infinity an integration from 0 to L of sine of lambda mx sine of lambda nx dx, and the result is equal to the integration from 0 to L of f of x sine of lambda mx dx, right? Now, this integration that you have on the left-hand side of the equation is equal to 0 if m is not equal to n, and it is equal to L over 2 if m is equal to n. So you can write an times L over 2 is equal to integration from 0 to L of f of x sine of lambda nx dx. We have written this integral to help you here. So an times L over 2 is equal to this, and we can say that an is equal to 2 over L integration from 0 to L of f of x sine of lambda nx dx, right? Now, please pay attention here. An is determined. What is left to determine? It is bn. But how do we determine bn? If we want to determine bn, we have to use the second initial condition. But the problem is that this second initial condition is given to us in the form of a derivative. We have rho over rho t of u at x and 0 is equal to f of x. But we only have u of x and t. So in order to be able to use the second initial condition, we have to calculate the derivative of u with respect to t, right? Now, u of x and t was equal to this. This was our conclusion at the end of step 2. This means that rho over rho t of u is equal to what? It is equal to sigma n from 1 to infinity. Now we have to derivate this with respect to u. We consider x to be a constant. We're going to have minus lambda n alpha sine of lambda n alpha t. And here we're going to have lambda n alpha cosine of lambda n alpha t. So the derivative of this sigma is going to become this sigma, right? Now that ut of x and t is equal to this, we can use the second initial condition, which was the initial velocity for it. Now, we put in 0 into this, and we're going to get rho over rho t of u at x and 0 is equal to sigma n from 1 to infinity bn lambda n alpha sine of lambda n x. And the result has to be equal to g of x, right? Now, here, lambda n is determined, alpha is determined, and when we want to determine bn, we have to multiply both sides by sine of lambda mx and integrate over the domain. If we do that, we're going to get bn lambda n alpha times L over 2 is equal to the integration from 0 to L of g of x sine of lambda nx dx. And from that, if we calculate Bn, we're going to have 2 over L times lambda n alpha times the integration. And now, considering that lambda n is equal to n pi over L, L times lambda n is equal to what? It is equal to n pi. Okay, so what am I saying? I'm saying that L times lambda n is equal to n pi. So we can say that Bn is equal to 2 over n pi alpha times the integration from 0 to L of gx sine of lambda nx dx, right? Now, if you want to summarize what you have here, we can say that the solution to 1D heat equation type 1 is this sigma an cosine of lambda n alpha t sine of lambda n x plus bn sine of lambda n alpha t sine of lambda n x, in which an is equal to 2 over L integration from 0 to L of f of x sine of lambda n x dx, and bn is equal to 2 over n pi alpha integration from 0 to L of gx sine of lambda nx dx, and lambda n is equal to n pi over L. So guys, questions? Everybody. Anybody? Azad, are you there? Azad, are you there? Jihad, are you there? Somaye, are you there?
Yes, sir.
So, guys, any questions? You naturally should have some questions at this point.